Hello everyone, my name is Yali. I'm glad to have you here to watch this video. Well, today I'm going to talk about one of my research papers, robust perimeter control with cordon queues and heterogeneous transfer flows. This paper has two more authors. There are Dr. Mohammed Yildirimoglu from the University of Queensland and Dr. Ramezani from the University of Sydney. This paper is published in a top-tier transportation journal, which is Transportation Research Part C, Emerging Technologies. And if you want to read it, please, you're more than welcome to. Okay, let's move to the research. Well, in this research, we proposed a perimeter flow control method that is traffic management method for large urban networks to effectively reduce traffic congestion as well as improve traffic mobility in urban cities. And further enables to reduce fuel consumption and air pollution. Okay, now let's see some relative terminologies. The first one is about two different representations of macroscopic fundamental diagrams, and let's call MFD for short. The two MFDs are accumulation-based and trip-based MFDs. So for the accumulation-based MFD, as shown in the top figure, it describes a nonlinear low-scattered relationship between trip completion rates and vehicle accumulations when the spatial distribution of congestion is homogeneous in the network. The trip-based MFD, as shown in the bottom figure, it describes a well-defined relationship between regional speed and vehicle accumulation of network. The trip-based MFD considers different traveler details, such as travel lengths, departure time, etc., whereas the accumulation-based MFD assumes all vehicles in a region with identical travel lengths. Okay, let's see perimeter flow control. It's a kind of traffic control approach that always apply on the region boundaries. As indicated in the right figure of a real urban network, the perimeter controllers are implemented between regions to manipulate the number of vehicles travel across regions. In this paper, we use a simplified network and use U12 and U21 denote the perimeter controllers. Actually, the perimeter controller is implemented through coordinated traffic signals installed at region boundaries between the regions to regulate the rate of transferring vehicles from one region to another to prevent hypercongestion. All right, let's move to the contributions of this research. Well, in this research, we mainly focused on three objectives. First of all, we developed an accumulation-based MFD model with uncertain parameters. Because in real network, there might be lots of uncertain parameters that influence the model accuracy. For example, when we estimate the accumulation fractions from one region to another, the number of transferring vehicles is approximated by the ratio of the instantaneous number of vehicles based on their destinations. This is the assumption used in accumulation-based model to estimate the transfer flows between regions. But we will release this assumption by including uncertain parameters. Then we develop a robust sliding mode control based on this accumulation-based model and apply the controllers on the trip-based model. So here the trip-based model is utilized to represent the real network to get more realistic values of transfer flows. Well, the control architecture further explain the role of each part. Let's see in this figure, the accumulation-based MFD is utilized as the model in order to design the real-time robust perimeter control, which is based on sliding mode control theory. And the two region trip-based MFD model is developed considering cordon queues that is regarded as the real network to investigate the performance of the proposed controller. So after introducing the two different MFD models, we need to ensure these two models are consistent since the controllers are designed and applied on different models. As shown in the figure, we utilized a slow varying demand, and the travel length follows exponential distribution. The accumulation evolution are shown in these two figures. The two models are consistent in the trend of accumulation evolution, while the magnitude are not exactly the same since the trip-based model reacts immediately when there are demand surge. Then we apply random selected travel lengths. The accumulation evolution of the two models are shown in figure A and B. We can see that when the system reaches steady states, like after 2200 seconds, the two models are consistent. We also compare the uncertain theta parameters as shown in figures C and D. Theta parameters are model uncertainties corresponding to the percentage of outflow. Remind that in the accumulation-based model, theta is continuous and estimated through instantaneous accumulations. But this estimation is not always accurate. While using theta to estimate accumulation fractions might be reliable under some under some conditions, but it is less accurate under time varying and complicated situations. So we need a robust controller to deal with the theta parameters. Okay, now let's see the controller performance. A typical peak hour demand is applied as shown in figure A, and the accumulation evolution of no control scenario is shown in figure D. As you can see in the figure, region 2 is the more congested region, since in no control case, the control inputs are always equal to the maximum values such that a few vehicles are queued at region boundaries. As you can see, the values of queuing accumulations are very low in no control case. The top two red figures, B and C, show the accumulation evolutions when applied improved bound controller and sliding mode control. And the figures E and F describes control inputs over time. As you can see, when applied improved bound control, the accumulation distributions are more uniform in two regions. But after 500 seconds, the vehicles are continuously concentrated at the region boundaries because of the perimeter controller. For the sliding mode control case, it can be seen that the congested region becomes region 1, whereas it was region 2 in no control case. This is because the sliding mode control tries to protect the more congested region 2. While perimeter control could ease the network congestion to some extent, but the cordon queue sizes are higher when applying either improved bound controller or sliding mode control, such that more vehicles suffer delay because of perimeter controller. The production MFD of region 1 and region 2 are indicated in these two figures. We can see the hysteresis loops in the figures. This makes sense since the hysteresis phenomenon exists when the vehicle accumulation is uneven distributed in the network. So in this paper, we consider cordon queues. So the distribution is not uniform, especially the queue size is large. The table shows the total time spent and average travel time for 3 control cases. The values in parentheses is shown the reduction in total time spent compared to no control case. As you can see, the sliding mode control gives the best performance, around 22% reduction in total time spent compared to no control scenario. Well, in summary, in this paper, a robust controller has developed based on sliding mode control theory to address modeling uncertainties in the accumulation-based MFD model. And also, a two-region trip-based MFD model is introduced and compared with accumulation-based MFD model. Then it is utilized as the real network to investigate the proposed controller effectiveness. And we found that employing sliding mode control theory outperforms the improved bound controller in reducing the total time spent. Okay, that's all my presentation today. If you have any questions or would like to discuss, please feel free to contact me. Thanks for watching.